Okay, so let's continue for our revision for our chapter of gravitation. So let's start with number one. Okay, a planet has a radius of 5,000 kilometer. So radius will be 5,000 kilometer. The acceleration of free fall is given as 6.05 milli per seconds. So what is the mass of the planets? So we have G is actually given as gm over r square. So G is actually given as 6.05 is equal to 6.67 times 10 to the power of negative 11. So this one will be our unknown. So this one is equal to 5,000 times 10 to the power of 3 square. So the final answer we get is actually equals to 10 to the power of 3 square, and this one will be divided by 6.67 times 10 to the power of negative 11. Okay, so the final mass we got is actually given as 2.268 times 10 to the power of 24. This is kg. Okay, so this is the first part. So as for the second part, the escape velocity of the planets. Okay, as we know that, as we discussed from the previous video, by saying that the total energy before leaving the planets is actually equals to the total energy after leaving the planets. Okay, so this one will be our gravitational potential energy. So from the surface of the planets, so r is actually given as the radius of the planets. Okay, plus half mu square. So this is our main concern, which is the escape velocity. So the total energy after leaving the planet is actually given as gmm over 2r. So I directly write this as the simplified total energy. Okay, so we know that at the infinity, if 1 over r is approaching infinity, eventually will approximately give us 0. So the whole total energy at infinity is actually 0. Okay, so gmm over r plus half mu square. Okay, so half mu square equal to gmm over r. So this one will be cancelled, and gm, we know that gm is actually given as r square g, which is g is equal to gm over r square. So gm will give us r square g. So this is how the r square g come from. Okay, this one is divided by r, so this one will be 2, so this one will remain u square. So u is actually 2gr. Okay, and finally we sub the information given by the questions, which is 6.05 for the g, and the r is actually given as 5,000 kilometers. So this one will be our final answer. So to 6.05, 5,000 times 10 to the power of 3. Okay, the final answer we got is actually given as 7.778 times 10 to the power of 3 milli per seconds. So this will be our part 2. The final answer is 7.778 times 10 to the power of 3. So this one we have done for the first question. So let's move on to our second question. So let me erase this one. Okay, this one as well. Okay, so we have done for the question 1. So let's move on to question 2. An object of the mass of 5.0 kg is placed on the surface of the Earth. Calculate each of the following gravitational field strength. So this is very simple. So gravitational field strength is actually given as G. So it's actually given as Gm over R square. So 6.67 times 10 to the power negative 11. Earth, the mass of the Earth given is 5.97 times 10 to the power of 24. Okay, so we are not about to use this one. Okay, what we use will be 6 sorry wait, okay, 6.02 times 10 to the power of 24 kg over the R square. Over the R square given is actually 6,400 kilometers, which is times 10 to the power of 3. So the final answer we get is actually given as 6.02 times 10 to the power of 24 divided by 6,400 times 10 to the power of 3. So the final answer is actually given as, how could be so big here? Okay, I forgot, here have a square here. So it's actually given as 6.67 times 10 to the power of negative 11, 6.02 times 10 to the power of 24. So this one will be 6,400 times 10 to the power of 3, and this one will be square. So the final answer we get is 9.80 newtons per kg. So this is our first part. So our second part will be the gravitational potential. So this one will be our negative Gm over R. So this one is 6.67 times 10 to the power negative 11. So the mass is actually given as 6.02 times 10 to the power 24. So this one will be our 6,400 times 10 to the power of 3. Okay, so our final answer will be 6.67 times 10 to the power of negative 11. So 6.02 times 10 to the power of 24 divided by 6,400 times 10 to the power of 3. Okay, so the final answer is actually given as negative 6.274 times 10 to the power of, let me count how many significant figures. There is 4 significant figures, and to the power of 5, 6, 7. To the power of 7 joule per kg for the gravitational potential, since it is the energy per unit mass. So this will be our part 2. So let's move on to part 3, and let me erase this one. Alright, so the gravitational attractive force. Okay, so very simple. We only sub into the formula. So as for the gravitational force, we know that for the calculation, so the negative is not required. So 6.67 times 10 to power of negative 11. Sorry. So the mass of the Earth is actually given as 6.02 24. So okay. So okay, 5.0 kg for the mass of the object divided by the radius of the Earth is placed on the surface of the Earth. So the distance between object and the center of the Earth is actually equals to the radius of the Earth times 10 to the power of 3 square. So this one will be 6.67 times 10 to the power of negative 11. 6.02 times 10 to the power of 34. So this one is 5. So divided by 6400 times 10 to the power of 3 bracket square. So the final answer we got is actually 69.02 Newton. Okay, so for the final parts, for question 2, so the gravitational potential energy is actually given as negative gmn over r. So this one is negative, of course, times 10 to the power of negative 11. So 6.02 times 10 to the power of 24. So this one is 5.0. So divided by 6400 times 10 to the power of 3 square. So negative 6.67 times 10 to the power of negative 11. 6.02 times 10 to the power of 24. 5.0 divided by oops, this one should not have square. Okay, so 6400 times 10 to the power of 3 bracket. So the final answer we get is actually given as negative 3.137 times 10 to the power of 8. Okay, so let me count again. Okay, yeah, and to the power of 8 joule. So this one will be our final parts for question 2. Okay, so let's move on to question 3. So let me erase this one. Alright, so this one is question 3. Okay, define Newton's law of universal gravitation. As we discussed from the previous video, Newton's law of universal gravitation. Newton's law, the name is quite long, of universal gravitation. States that the gravitational attractive force I prefer to write gravitational attractive force since it looks very clear. Should I set that? Okay, attractive force is directly proportional to the product of the two masses and inversely proportional to the square of distance between them. So this is the statement for the Newton's law of universal gravitation. As for the relation, okay, gravitational force is directly proportional to the product of the two masses and inversely proportional to the square of distance between them. So this is R. Okay, so this is for question 3A. Okay, so let's move on. Okay, so let me erase this one. Alright, so as for B, okay, a satellite with a mass of 1337 kg. So let me check whether it is correct. I'm afraid the value is wrong, so let me check again. So which question is this? Okay, okay, so yeah, the value is correct. Okay, it's initially orbiting the planet Mars at the altitude of okay, so this one will be height times 10 to the power of 3. So gradually descend to the lower altitude of, okay, this one will be our H1, so this one will be our H2. 316 times 10 to the power of 3 meters. Okay, so calculate the potential energy at initial altitude. Okay, so yeah, the potential energy at initial altitude. So we know that U is actually given as negative gmn over R. Okay, so but this one indicates the altitude from the surface of the Earth, so the distance must be added with the radius of the Earth. So this one is actually given as gmm. So this one R will change to R, which is radius of the Earth, plus the altitude which the satellite's located. Okay, so this one is negative 6.67 times 10 to the power of negative 11. So the mass of the Earth is given, the mass of the Mars, sorry, is given as 6.42 times 10 to the power of 23 here. So our satellite mass is actually given as 1337. Okay, so this one is not radius of the Earth, should be radius of the Mars. Okay, so radius of the Mars is actually given as 3.39 times 10 to the power of 6 plus the altitude which the satellite located, 0 times 10 to the power of 3. Okay, so the final answer we get is given as 6.42 times 10 to the power of 23. So 1337 for the mass of the satellites divided by 3.39 times 10 to the power of 6 plus 45000 times 10 to the power of 3. So the final answer we got is actually given as, okay, so Okay, I'm wondering why the answer is different. So let me check whether my value is wrong. Okay, the final answer given is actually 1.18 times 10 to the power of 9. Okay. Well, of course negative, but my final answer is actually given as 1.263. Okay. 5, 6, 7, 8 times 10 to the power of 8. So that's strange. So let me find out which part I got wrong here. So the potential energy at initial altitude should be given as 4000 kilometers. Yes, correct. Okay, so initial altitude, yes, 6.42 times 10 to the power of 23, 1337 for the mass of the satellites. Okay, let me check whether there is typing error. So 3.39 times 10 to the power of 6. Okay, so okay. So alright, 45000 plus 3.39 times 10 to the power of 6. Yeah, the answer shown here is correct. Okay, I wonder where did I got wrong. 6.67 times 10 to the power of negative 11. 1377 times, okay, 6.42 for the mass of the mass, okay, times 10 to the power of 23. So 4.839 times 10 to the power of 7 for the radius of the Earth plus the altitude which the satellite is located. Okay, so the final answer we get is actually given as, okay, so yeah, I think the answer wrong here. There's an error for this answer. So the final answer we got is actually given as negative 1.263 times 10 to the power of 8. Okay, so let me recheck again. Oh, that's a problem here. So let me recheck again. Alright, where did I got wrong? 6.67, okay, 22, okay. So the distance will be the troublemaker. 10 to the power of 6, 45000 times 10 to the power of 3. So okay, so the answer is correct, but I'm wondering why the final answer is different. Okay, right, let me retype again in my calculator. So 1337 for the mass and 6.42 times 10 to the power of 23 divided by 4.839 times 10 to the power of 7. Okay, So yeah, oh, I think there's an typing error for my calculation just now, so the final answer should be this one. Yeah, this one. Alright, so the final answer is actually given as negative 1.18 times 10 to the power of 9. Okay, so I apologize for my mistakes. Okay, so the change, so let's move to second parts. So the change in energy during descent. Okay, so let me erase this one. Okay, so the change in energy, we know that the wait the change in energy, this energy is actually meant by the total energy, which means that ET2 subtracted by the initial energy, initial total energy. So negative GMM over R2. Oh, sorry, this one is 2R2 for the total energy. So the subtract by the GMM 2R1, which is the total energy for the initial location of the satellites. So this one is factorized here. So this one over 2, and oops, I should simplify the negative part first. Okay, so this one negative is actually positive. So GMM over 2R1. Okay, so negative GMM over 2R2. So and we just factorize this one, GMM over 2. Okay, this leave 1 over R1 minus 1 over R2. Okay, so we just substitute the value into this formula, 6.67 times 10 to the power of negative 11. So the mass of the mass is given as, okay, let me recheck again in case there's typing error for me again, of 23. So the mass of the satellite is actually 1337 divided by 2. Okay, there's not enough space, so I write it here. So the initial distance is given as, so the initial distance is initial distance is, okay, so the change in energy, okay, so 45000 times 10 to the power of 3 plus the radius of the mass. Okay, the radius of the mass is actually 3.39 times 10 to the power of 6. Okay, subtract by 316 times 10 to the power of 3 plus 3.39 times 10 to the power of 6 for the radius of the mass. Okay, so what will be our final answer here? 6.42 times 10 to the power of 23, 1337 divided by 2, 1 over 45000 times 10 to the power of 3 plus the radius of the mass Wha- 1 over 316 times 10 to the power of 3, okay, plus 3.39 times 10 to the power of 6. So the final answer we get is negative 3.133 times 10 to the power of 3, 4, 5, 6, 7, 8, 9. Okay, the final times 10 to the power of 9. So this is joule. So the change in energy during descending is actually equals to negative 3.133 times 10 to the power of 9 joule. So this is the second part. So let's move to the third part. So this is question 3. So calculate the orbital speed after descent to the altitude of 316 kilometer. Okay, so the question required for the orbital speed, eventually we will think of the centripetal force, which is the orbital speed. It means that the satellite is about to undergo circular motion around the planet Mars. Okay, so this one will be mv squared over r is actually given as gravitational force, which is the only force acting on the satellites. So this one is g. Okay, this one will be cancelled, and this one will be cancelled, and find and leave only one r. So gm over r. So v square. So this gm depends on the students whether wish to change to r squared g or not. But here we have the mass of the Mars is given, so we can directly sub the value 6.67 times 10 to the power of negative 11. So mass of the Mars is actually 6.42 times 10 to the power of 23. So the radius for the satellites, the radius of the orbits, which is the altitude 316 times 10 to the power of 3 plus the radius of the mass, okay, of the mass 6.42. Oops, this one is the radius, this one is the mass. So the radius of the mass is 3.39 times 10 to the power of 6. So okay, let me drag down. So the final answer we got is actually given as 6.67 times 10 to the power of negative 11, 6.42 times 10 to the power of 23, divided by 316 times 10 to the power of 3, plus 3.39 times 10 to the power of 6. Okay, then the whole answer is adding the square roots. So the final answer we get is actually given as 3.40 times 10 to the power of 3 milli per seconds. So this is how we answer for the orbital speeds. Okay, so we have done for the third questions. So let's move on for the number 4. Okay, I hope you can understand. If there is any question need to be asked, or some explanation made you confusing, you can comment on this video below. So let's move on to the number 4. A satellite of mass 50 kg is launched from the surface of the Earth. So this one is the keywords: from the surface of the Earth to the geostationary orbits. Calculate the angular velocity of the satellites. So angular velocity means that there is a circular motion here, so mr omega square is equal to the gravitational force, which is the only force acting on the satellites. Okay, as same as the question number 3. So this one is the radius of the Earth, okay, a satellite, okay, to geostationary orbits. Okay, so let me think about it. Angular velocity. So the angular velocity here is okay. This radius I confusing about whether this distance is the radius of the Earth or the geostationary orbits. I think it's the radius for the geostationary orbits, but how can we find this? Or it may require the other formula, so let me think about it. Okay, the angular velocity. Angular velocity. So let me check about it. Oh yeah. Okay. So the angular velocity. Okay. So since we did not have the radius of the geostationary orbits, so we cannot. This formula is not applicable. So we need to find another alternative way. Okay, so we know that the angular velocity is equal to the 2 pi over t. So this t is for the satellite to complete one circle. So since the satellite is at the location of the geostationary orbits, and we discussed about the geostationary orbits from the previous video by saying that the period of revolution for the satellites, revolution of satellites is equal to the period of revolution of the Earth. Revolution of the Earth. Alright, so period for revolution of the Earth for one complete circle. Okay, so period of revolution means of the Earth for one complete circle means 1 day for the Earth. So 1 day for the Earth is actually for we have 24 hours for 1 day times the 60 minutes times 60 seconds. Okay, so this 2 pi over 24 times 60 times 60. So the final answer we get for the angular velocity is actually given as 7.272 times 10 to the power of -5. So this is radian per seconds. Alright, so this one is question part 1. Okay, so this one will be our radius of geostationary orbits. Okay, so the in order to find the radius of geostationary orbits, so this formula as I written from the previous question is now applicable. So gmm over r square. So this one will be cancelled, and this one will be r cubed omega square, and this leave gm. Okay, so we know that the mass of the Earth, okay, so wait a second. So the mass of the Earth given is Okay, I think, okay, the mass of the Earth 5.97 times 10 to the power of 24. Sometimes the mass of the Earth is quite different. Okay, so I just write this constant for the mass of the Earth. Okay, so we need to find the radius, so the radius will be our unknown. So the angular velocity we found just now is 7.272 times 10 to the power of negative 5 square. So the final answer we got is actually given as 5.97 times 10 to the power of 24. So divided by 7.272 times 10 to the power of negative 5 square. So the final answer we got is actually, well, wait, there's another mistake here. Okay, so where did I got wrong? Oh, I forgot to cube roots the radius. Okay, so the final answer we get is actually given as 3, 4, 5, 6, 7. Okay, so the final answer is 4.222 times 10 to the power of 7 meters. So this is the geostationary orbits for our satellites. Okay, so for the third question, okay, let me erase the first question here. Alright, so the third question, the change in gravitational potential energy. So we know that change in gravitational potential energy is actually given as the final gravitational potential energy, which is located as at the stationary orbits, okay, minus the initial gravitational potential energy, which is on the surface, okay, on the surface of the Earth. So this counted as the radius of the Earth. Alright, okay, so let me bracket this one. Okay, then we resolve the negative parts, so this one will be positive over R minus GMM over the radius of the orbits. Okay, so geostationary orbits, so this one will be factorized. Okay, bracket 1 over RE minus 1 over RS. Alright, so this one is 6.67 times 10 to the power negative 11. So the mass of the Earth given is 5.97 times 10 to the power of 24. Okay, so the mass is 50 kg for the satellites. So this is the radius of the Earth. So the radius of the Earth given as 6,400 times 10 to the power of 3 minus, okay, the geostationary orbits we found just now is 4.222 times 10 to the power of 7. Alright, so this will be our final answer, which is negative 11.97 times 10 to the power of 24. Okay, 50 1 over 6400 times 10 to the power of 3 minus 1 over 4.222 times 10 to the power of 7. So the final answer we get is actually given as okay, so 2.64 times 10 to the power of 9 joule. Okay, so this is the final answer. Alright, so let's move to the final question. So let me erase this one. Okay. Okay, change in kinetic energy. So what is change in kinetic energy? So we know that the total energy before leaving the earth is equal to the total energy after leaving the earth. So this is the potential energy uh, at the surface of the earth plus half mv square mu square. So this is the initial velocity. Okay, this one will be the gravitational potential energy at the radius of the stationary orbits, which is denoted as s. Okay, so this one is our final velocity. So this is mv square. Okay, so the question asks for the change in velocity. So half mv square minus half mu square, which this one is dragged into here, dragged to the other side. So gmm over rs minus gmm over r. Okay, so we can see that the change in kinetic energy is actually equals to the negative change in potential energy. So why should I say negative? This is because 1 over rs, 1 over small letter rs minus 1 over capital letter re is actually given as negative, since this one give us the positive value, and so this one will give us the negative value. So it's actually equals to negative 2.64 times 10 to the power of 9 joule. So this is our change in kinetic energy. So why there is negative here for the change in kinetic energy? Okay, so let's say I draw a rocket. Okay, as the rocket is launching from the surface of the earth, so until this point, which is the stationary orbits, the change, okay, the kinetic energy is about to change to potential energy from here when the rocket is launching until the rocket stop at this location. So finally the energy is converted to gravitational potential energy after the rocket stops here. It means that the gain in gravitational potential energy is actually equals to the loss in kinetic energy. So that is why we got the value for the kinetic energy, which is negative. So this is how we determine the final kinetic energy at which all the gravitational potential energy is completely converted after the rocket stops here by saying that all the kinetic energy is converted to gravitational potential energy completely after the rockets approach the geostationary orbits. Alright, we have already completed for the 4 questions. So I think we stop here and we will see in the next video. So if there is any question need to be asked, so please comment below of this video. So I'll see you in next chapter. So thank you. Bye.